Sharath and I'm from the National Institute of Technology, Calicut, India. I'm very happy to present my work here exploring pH sensing in MoS2-based ISFETs with 2D, 3D gate oxide stacks. So this is the brief overview of my presentation. I'll give an introduction, then there will be an ion sensitive field effect transistor working as pH sensor, then 2D ISFET utilizing 3D oxides as a sensing element, dielectrics for 2D, TMD-based FET pH sensor, TCAD and compact model of ISFETs, results and discussions, and finally the conclusion. So as we know that as the healthcare management, there's a shift towards effective as well as effective shift towards the rapid detection of early detection of diseases. So there should be devices which are cost effective, wearable, low power, and miniaturized point of care devices are essential for early disease detection. So here we have field effect transistor, material-based biosensors. They are capable of detecting biological molecules, which is actually the biomarkers which can be an indicator of an underlying disease condition or contaminations. So researchers have found that bio-FETs with low dielectric layers enhances the response time and stability, making them ideal for point-of-care applications. So here in bio-FETs, we use, we are concentrating on atomically thin TD-2MDs, which is transition metal dichalcogenides. They are found out to be an ideal material for next generation bio-FETs because of their high surface to area volume ratio, sensitivity, selectivity, and seamless integration with CMOS technology. So here, what I'll just give you a brief introduction about what you mean by the ion-sensitive field effect transistor and how it works as a pH sensor. So you can see that if you see the structure of an ISFET, it is basically looks like a MOSFET, and the only difference is that you replace this metal electrode with an electrolyte with a reference electrode immersed into it. So this is the structural difference. And when you have, what you are trying to do is you want to detect the pH value of the electrolyte solution. So the basic mechanism is like this, that this pH sensing is based upon, there will be oxide and there will be oil surface groups on the surface dielectric layer. So when you change the pH of the electrolyte solution, there can be protonation and deprotonation happening at this oxide surface layer, and there will be a surface charge based on that. Net surface charge will be there. So that surface charge, together with this applied electrolyte gate potential that you apply here to the reference electrode, will give you a surface potential. That surface potential will be translated to the conductance of the channel. So there will be a change in the drain current. So this drain current will be an indicator of the change in the pH of the electrolyte solution. So you can see that sensing surface, you can see there can be a change surface potential, mobility, carrier scattering, etc. And it can be translated in the form of drain current variation, threshold voltage variation, or transconductance variation. So you can see that this is the basic equation for sensitivity. That is, when you change surface potential, which results as a change in the pH, you can get minus 2.3 alpha kBT by Q. When the alpha is given by this equation, where the Cs is the electrical surface capacitance and beta S is the intrinsic buffer capacity. When the alpha value reaches equal to 1, you can get the maximum sensitivity. It will be approximately equal to 59.6 millivolt per pH. That we call as the Nernst limit. For single gate structure, that is the maximum limit sensitivity that we can achieve. So here, our problem lies in, because since we are using a 2D material like MoS2, that is 2D TMD like MoS2, there will be the oxide, that top dielectric oxide that we are using is HFO2 or Al2O3 or a combination of 3D oxides. So these 3D oxides and 2D channel. So that means that the interface between this 2D oxide 2D channel and 3D oxide, there will be interface traps. And that's for any device, if there are interface traps, it will deteriorate the device performance. So there can be charge scattering, there can be that will affect the on current. There will be interface states which can result in hysteresis, and there can be gate leakage also. So because since we are using a 3D oxide and a 2D channel, that will result at the interface, there will be interface trap states. So the problem that we identified as, since this 2D ISFET is having a 2D FET as the baseline transistor, you will be having an issue of interface traps at this interface, 3D oxide bar 2D semiconductor interface. So that is the issue that will deteriorate the performance of the device or the sensitivity of the device. So what can be done? So what we are proposing is, That is, instead of this interface, if we can remove that interface, like with 3D oxide and 2D channel, if we can have 2D channel and 2D oxide, then we can have a better interface. So we have to find out some dielectrics, or we are in search of dielectrics which are compatible with this 2D TMD FETs. So researchers are working on that, and there are many studies that this 2D layered dielectrics, which are an excellent fit for this 2D TMDs. As you can see that here, there are many 2D layered dielectrics which are having low leakage current density and EOT is very low. And there are some advantages of 2D dielectrics over 3D dielectrics in the case of with respect to 2D channel. You will have a smooth dielectric bar semiconductor interface. You will have minimum inefficient trap states, and it will eliminate the surface scattering, thereby enhancing the on current and mobility of the channel. So the proposed solution that we are having is, instead of a 3D oxide at a 2D channel, we replace that with a 3D by 2D gate oxide with instead of a 3D oxide, and we are trying to see that if it will exhibit a pH sensing, and it will eliminate the interface trap densities and interface traps, and thereby enhance the sensitivity. So the basic workflow is like we will develop, we do this, we are not into fabrication, we are like modeling this device. So we have a numerical TCAD model as well as a compact model. In what we are doing is, first we initially create the 2D ISFET with 3D oxide, and then we use a TCAD model, calibrate with the experimental data, a compact model, calibrate the experimental data. And then we when we do a structural modification, that is, we replace this 3D oxide with 3D by 2D interface, gate stack. So what we are trying to do is, there is a TCAD model we develop using Silvaco Atlas tool, that is 2D material-based ISFET. Here we have 3D oxides, and we have the MoS2 as a channel. So the tool we are using is Silvaco Atlas, and you can see that we change the effective density of states with respect to the pH of the solution. So as you can see, the electrolyte is represented as modeled as an intrinsic semiconductor. And why it is so? Because the charge distribution inside this electrolyte follows the Poisson-Boltzmann distribution, so that we can conveniently model it as an intrinsic semiconductor. And the models that we are using for this simulation are SRS, that's Shockley-Rithold combination, Aurora mobility model, and the field mobility model. And you can see here, that is, you can see there is a VFG and the voltage and the current plot. And when you change the pH values, there's a shift in the ID values. That is, as I told in the beginning, that is, when you have an ion sensitive field effect transistor, when you change the pH of the solution, what will happen is, there will be, at a lower pH, what will happen? Lower pH, there will be an protonation. There will be protonation of the OH groups, and that protonation leads to excess positive charges, thereby reducing the threshold voltage. Here, when you increase the pH of the solution, what will happen is, you are trying to deprotonate. The OH groups will be deprotonating, and thereby threshold voltage will be increasing, and you can see there is a shift, there is a decrease in the drain current. And this is validated with the experimental data. That is, the symbol represents the experimental data, and the line represents the TCAD. So it's very decent like fitting that we can get, we got from the experimental data. So in this way, we calibrated this TCAD setup for modeling the 2D material-based ISFET. Secondly, we developed a compact model for a 2D material-based effect based on the equations, physical-based equations. So here the structures remain the same. You can represent it using a macro model. That is, there are two decoupled circuit elements over here. That is, the electrolyte is represented with a voltage, the surface potential is represented here which is pH dependent. And then you have the baseline transistor here, baseline FET, it's a MOSFET. So what we are trying to do is, the effective gate potential. That is, when you change the pH of the solution, you will be having a change in the surface potential. So the effective gate potential that is going to affect at the baseline FET, and thereby you change the drain current. Okay. So when you change pH of the solution, surface potential will change, and then effective gate potential of the FET will change, and there you will get a change in the drain current. So this is the compact model. Only the relevant equations are shown over here. So you can see that the VG effective, which is the gate potential, effective gate potential applied at the baseline FET, that will be VFG minus I0, and this I0 depends upon the pH. and this I0 is actually depending upon this value pH. The rest are all constants. This delta W is nothing but the intrinsic buffer capacity, that is it's calculated using the intrinsic buffer capacity, which indicates the change in surface charge due to the change in pH. And this is from this what we can do is when you change the pH of the solution, you get what is called the surface potential, and this surface potential will be reflected in the gate potential, and then you have the baseline FET. So we need to model the baseline FET. So as we are using a 2D like double gated FET, there you have the charge density over here, that is Cox into that is the basic Gauss law. From the Gauss law you get this equation where Cox represents the gate oxide top gate oxide capacitance, and Cbox represents the bottom gate oxide capacitance, and Vt is the threshold pruning voltage parameter, and phi s is the surface potential, semiconductor potential. And we can also represent using Fermi-Dirac statistics what is the charge in the charge density, and this will be like QBT NDOS, and then this equation will be there, and this NDOS is the effective density of the states, and V is the quasi Fermi potential, and Vth is the thermal voltage. Equating these two things, what you are trying to achieve is the surface potential, that is the phi s. And phi s is taken as an initial solution, initial surface potential, and when we can find out what is the surface potential at the source and the drain by putting V equal to 0 and V equal to VDS. Since source is grounded and V equal to VDS, we get at the source and the drain what is the surface potential. And utilizing this surface potential, what we are trying to achieve is the drain current, that is the IDS. So you change pH, you change surface potential, and corresponding effect is reflected in the drain current. So here we are particularly concentrating on interface traps. So we need to include those interface traps also into the charge. So the effective charge will change accordingly, and this effectively charge again the same process, and then you will get a different current because of the effect of the interface traps. So this is basically the compact model. Only the relevant equations are shown over here, and then we have to validate whether we need to know that whether this model is correctly performing or behaving and giving the correct results. So we need to validate this model with the experimental data. So we are able to understand that, okay, when you change the pH, as earlier I have shown you, this is the experimental data, and this is basically the model. We implemented this in MATLAB, and we call that experimental and model behavior in the linear and the logarithmic schemes, and its behavior is as expected. And now the thing is that we need to change the interface to 2D by 3D gate oxide stacks. It is just a proposal. That means like we don't have the experimental data out of it. It's just our proposal. So what is happening is you replace this gate electrode with a stack of 2D and 3D. So the 2D oxide here we have used is lanthanum oxychloride, which we found out from the literature that it is having interface trap field defects with MoS2. Many studies are there. So we have taken 2D oxide, the lanthanum oxychloride, and then we performed the TCAT study first to generate this data set, and then it is validated with the model that we have already developed and validated. So we can see that excellent validation have been obtained within IDS and VFG with the IDS as well as the GM. And this is the parameter values that we have taken for this validation. And finally,
please note that the time is up, so please wrap up.
Okay, that's one more slide, sir. So in sensitivity analysis, we can finally got that where when we use 2D and 3D gate oxides and 3D oxide, you get a much better sensitivity with 2D bar 3D gate oxide stacks. And finally, the conclusion that we get a better, interface traps are required. We need to eliminate those things. And this is our proposal that replacing 2D with 3D with 2D, 3D gate oxide stacks.
All right, let's thank our speaker.